All right. Okay. So Ninja's here. Welcome, everyone. We're ready to get started. So it's a pleasure to have all of you here joining us for the last TCS Plus of the semester. Unfortunately, we're already there, but we're very pleased to have Erik Waingarten from Columbia University to give the talk. So before I introduce Erik some more, maybe Ninja, you want to quickly go around the table and say hi to all the groups who are joining us?
Yeah. So the group from we have the group from Caltech, led by Arnaud. Hey, then we have the group from Columbia, led by Clement. The group from Wisconsin, led by Dimitri. The group from USC, led by Ehsan. Then we have the group from VCU, led by John King. I can't. Okay. K. Gopalakrishnan from East Carolina. Okay, so we have, and then the group from NYU, Shavaswal, the group from Michigan, led by Sina. Srinivasan from, well, actually, sorry, I don't have, which place are you from? I'm sorry, I don't.
CWI.
Oh, CWI?
CWI. Yeah. Yeah.
Hey, and finally, we have Varun from IIT Guwahati. Okay, so over to Thomas.
Great, thanks in India. So let me also acknowledge everyone working behind the scenes. So there's an India Day here, but also Detregev, Clément Canon, Gautam Kamat, and Ilya Rasenstein working behind the scenes to bring you the best speakers of 2017. And the last one of the list, but not least, of course, is Erik Waingarten. So welcome, Erik. Erik is a second-year PhD student at Columbia University. His advisors are Rocco Servedio and Si Chen. So welcome. And Erik is going to tell us about new results to be presented at the next talk on the query complexity of junta testing. So thanks, Erik. Erik, I don't know if you're speaking, but I cannot hear you. Unmute yourself, maybe. Sorry, is this just me or Ninja? Can you hear Erik?
No, I can't hear him either.
Okay. Erik, we can sort of see your slides, but actually I cannot see anything.
No, sorry, I can't see anything either.
Okay, we don't have a speaker. Okay, Erik, I don't know if you can hear us, but if you can, maybe the easiest is just to get out and join again. So one, I guess summer is not the time that you make resolutions, but one of the resolutions we're making for next semester is, I think, to drop Hangouts and try to find a better format, because it's been, I think Google is retiring the Hangouts thing. And so there's changes every time we use it, and we're having more and more technical glitches. So we apologize for that. We'll try to make it better next semester. For today, though, let's hope Erik manages to join again.
Okay, Erik has joined. So should he be kept on the presentation mode?
Erik, we can see you now.
Can you hear me?
Yeah.
Okay, great.
Maybe you can try to screen share.
Yes. Can you see everything okay?
Yeah, it's very good.
Okay, great.
So maybe full screen. All right. Okay. Sorry, everyone, about this. Welcome back, Erik, and go for it.
Oh, so. Okay. Great. Well, thanks for inviting me, and I'm very happy to be speaking here. And today I'll talk about the query complexity of non-adaptive junta testing. And I'll mention this is joint work with Shi Chen, Rocco Cervedio, Liang Tan, and Jin Shi. Okay, so we'll talk about Boolean function property testing. And in this model, we have some player, Alice, who has a black box access to some unknown Boolean function f. And she gets to make queries to these Boolean functions to evaluate this function at some particular input. And the goal here is to come up with randomized algorithms that can tell if f has the property p or f does not have property p. And maybe it's not hard to see that the way that I've defined this problem, the problem becomes extremely hard. So for instance, if we consider the simple property just consisting of one function, which is a constant zero function, then it's not too hard to see that in order to test this property, we'll need to make around 2 to the n many queries. And there's sort of these hard inputs, these Boolean functions, which are 0 everywhere, except for at some hidden point A. And the idea here is that if Alice wants to sort of reject these functions that don't have the property, that aren't constantly 0, she'll need to find this hidden point A. And in order to do so, she's going to need to query 2 to the n many points. But sort of this is too bad, because with 2 to the n many queries, we can simply just query the whole function. So in order to address this issue, people have proposed to look at some approximation versions of this problem, where now we have this player Alice, and she wants to distinguish between the following two cases. Either f has a property p, or f is sort of far from having this property p. And this is shown nicely in this diagram, where we have here the universe of all possible n variable Boolean functions, and then this innermost blue circle will correspond to the Boolean functions with property p, and this outermost green circle would be the Boolean functions which are far from having property p. So, okay, what do I mean by sort of a function being far from a certain property? Well, we'll work with having the distance between two functions being the probability that they disagree on a uniform random input. And now we can say that the distance between a function to a particular property, this will be the closest distance to any function with that property. So I'll commonly say that a function is epsilon far from a property p. This will just mean that the distance between f and the property is at least epsilon. Or another way I think about it is that if I wanted to change some inputs of my function f so that it has a particular property, what's the minimum number of inputs that I need to change? And this is the fraction of inputs I need to change. Okay, so to review sort of the rules of the game, we have Alice, who has access to some unknown Boolean function, as well as this parameter epsilon, which is sort of the approximation factor. And we need to come up with a randomized algorithm which has the following guarantees. If the unknown function has a property p, or lies in this innermost blue oval, then the algorithm should accept with probability at least 2/3. If f is epsilon far from having this property p, or lies outside in this green region, then the algorithm should reject with probability at least 2/3. And otherwise, if it lies inside this gray slab, then it doesn't matter what the algorithm outputs. And the main question we're interested in is to find the minimum number of queries that we need in terms of both n as well as epsilon. Now I'll mention that sort of this area of property testing falls within this larger umbrella of super efficient algorithms, where in this case we're trying to establish randomized algorithms which optimize the time or the number of queries we make, similar to data structures. But we have models for optimizing sublinear space, such as streaming and sketching, and other models for which we care about optimizing the number of measurements, such as in sparse recovery and compressed sensing. And the two notable facts of this area of property testing is that many properties here were testable with very, very few queries. So in particular, we'll be able to come up with algorithms sometimes for which the number of queries is completely independent of the size of the object. And the second notable fact is that studying these kinds of questions has led to many rich connections to other areas in theoretical computer science, such as learning theory, hardness of approximation, and communication complexity. But okay, so for this talk, I want to focus on the case when the property of being a K-junta. So P property will be a family of properties of being K-juntas. And so what does this mean? We'll say a Boolean function f of n bits is a K-junta if it depends on at most K variables. So let's simply go through some simple examples to get a good feeling of what this property is. So this function f of x equals xi and xj, and this is clearly a 2-junta, since even though the function depends on n many bits, in order to evaluate the function, we only need to read bits I and bits j. So okay, for an example of a function which is not a K-junta, we'll have this function which is a uniform random function. So a function for which each input is set to 0 or 1 with probability 1/2. Now it's not hard to see that this function will actually depend on all inputs. So if k is less than n, this function will not be a K-junta. And in fact, if we wanted to remove the dependence on any single one variable, then we'd need to change a constant factor of the hypercube. So in fact, these uniform random functions with very high probability, they'll be constant far from even n-1 juntas. And lastly, maybe a little more subtle, is this function where we take the majority of k+1 bits. And here we can see that we actually need to read k+1 many bits, so the function is not actually a K-junta, because there's cases for which each bit will have some say in the value of the function. In some sense, this last bit will be the tiebreaker in the majority. But it turns out that the number of times in which this happens is actually quite small. It'll turn out to be around order 1/√k fraction of the hypercube. So we'll consider this function as being sort of close to being a K-junta, even though it's not a K-junta. Okay, so let me try to analyze this one specific case of one junta testing. So the main question here is how many queries are needed in order to distinguish between Boolean functions which are 1-juntas and Boolean functions which are epsilon far from being 1-juntas with probability at least 1 minus delta. And maybe I've disguised the problem a little bit, but this problem has been very well studied, and in fact, this is also known as a problem of dictatorship testing. Because any one junta can either be a dictator or an anti-dictator. And in fact, this problem has been studied a lot and has nice connections to proving hardness of approximation. This was established by Belair, Goldreich, and Sudan in '98, and was later studied by Parnas, Ron, and Samrodnitsky in 2003. But okay, so before we move on to analyzing algorithms for testing K-juntas, I want to make the distinction between two classes of algorithms in property testing. This will be between non-adaptive and adaptive algorithms. So I'll first describe the non-adaptive algorithms, and these are represented in this diagram. So these algorithms will be one-round testing algorithms, and you can think about these as being highly parallel testing algorithms. So the way in which they work is Alice will first flip some coins, generate some randomness, and she'll come up with a list of queries x1 through xq, and she'll send these queries to the Boolean function f. At which point, the Boolean function responds with the values of all the queries that she made. And after this one round, now Alice must say whether she accepts the function as having the property or she rejects the function. And it's easy to see. So these algorithms proceed in one round. They're very parallel. All the queries are done before. And the reason why we say that it's a non-adaptive algorithm is because the questions that Alice makes cannot depend on the information that she gets about the unknown Boolean function. So this is in contrast to, say, adaptive algorithms, where the algorithms will proceed in queue rounds. So in particular, Alice will make the query x1, and then the function will give her the value of x1. And then now Alice can make query x2, and she can pick the query for it to depend on the value that she received on f of x1. And sort of this procedure will go back and forth between the function and Alice for at most Q rounds, where she makes the last question, gets the final response, and now she may output whether she accepts or she rejects. And maybe it's not hard to see that adaptive algorithms are more powerful than non-adaptive algorithms. In fact, we can say that an adaptive algorithm with Q queries can simulate any non-adaptive algorithms with Q queries, because the adaptive algorithm may simply choose to forget about the answers to the queries until the very last round. So adaptive algorithms can only be more powerful than non-adaptive algorithms. And in the other direction, we have this other relationship where non-adaptive algorithms with 2 to the Q queries can simulate adaptive algorithms with Q queries. And this is because a non-adaptive algorithm can simply prepare for all possible responses that the adaptive algorithm may give. And so with making all 2 to the Q many queries, she can then simulate the adaptive algorithm by giving whatever answers she needs to the adaptive queries. So okay, so we know that adaptive algorithms in general are more powerful than non-adaptive algorithms, but this gap can be at most an exponential factor. And what's maybe surprising is that for some natural properties of Boolean functions, these exponential gaps are known. These are some examples are for testing signed majorities, as well as testing read once with 2 branching programs. So okay, let me try to convince you that adaptivity may help a lot in property testing. And the key word here is binary search. So in order to show this, we'll assume that Alice has access to some unknown Boolean function f, and we'll describe this Boolean function as this hypercube here on the right. So let's suppose that Alice picks 2 random points in the hypercube, x and y, and these 2 points happen to fall in parts of the hypercube where their values of f disagree. So let's say that this value is x and this value is y, so f of x equals 1 and f of y equals 0. Now what Alice can do is she can consider an arbitrary polynomial length path in the hypercube between x and y, and she can query the middle point. And in this case, this point z has value of 0, so now what she can do is she can recurse on the side which has the endpoints of the path disagreeing. And since each time we're cutting the path by half, after log n many steps, she'll come across an edge in the hypercube. So some points are at the distance of 1, which their function values disagree, and they're in some direction I. So what does this mean? That after log n many queries, we can sort of find one important direction. So this is something that this procedure is a very adaptive procedure, that we need to know the value of z before we choose whether we recurse on the left side of the path or on the right side of the path. Okay, great. So talking about upper bounds, the main question that comes to mind is, can we even test k juntas with query complexity that's independent of n? So remember that the Boolean function is a function on n bits, so we can sort of the size of this object is 2 to the n. It's a string of length 2 to the n. And can we determine whether it's a k junta with the number of queries that's completely independent of the size of this object? And the answer here is yes. In 2004, Fisher, Kindler, Ron, Safra, and Samrudinsky, they showed that we can epsilon test for k juntas for any k with poly k epsilon many queries. And in particular, they give a non-adaptive algorithm with complexity which is k squared over epsilon. So this was in 2004, where they showed that in fact the dependence on n is unnecessary. And then in 2008 and 2009, Erik Waingarten was able to improve on this algorithm in both the adaptive as well as the non-adaptive models. So in particular, he shows that there exists a non-adaptive algorithm for testing k juntas, making k to the 3/2 over epsilon many queries. And then in 2009, he showed that there exists an adaptive algorithm which tests k juntas, which makes k over epsilon plus k log k many queries. So okay, and at a very high level, sort of the way these algorithms work is that the non-adaptive algorithm will estimate this quantity called variation on certain blocks of coordinates, and the adaptive algorithm will use a similar strategy to this binary search method that I described earlier on certain blocks of coordinates. And okay, so now we have some improved algorithms for testing k-juntas in both models. And what do we know about lower bounds? So in 2004, Chuckler and Gertfront showed that testing juntas, possibly adaptively, requires order k many queries for some constant epsilon. And then in 2013, Berman, Garcia, Soriano, Matzlia, and DeWolf showed that testing juntas non-adaptively requires k log k many queries for some epsilon. So summarizing the upper and lower bounds for both the adaptive and non-adaptive ways, we have the following table. In the non-adaptive model, we have an upper bound k to the 3/2 over epsilon and a lower bound of k log k. And in the adaptive algorithms, we have a k over epsilon plus k log k upper bound and an order k lower bound. So by looking at this table, the first thing to notice is that even though in general the power of adaptive and non-adaptive algorithms can be at most an exponential, for the specific case of k-juntas, we have at most a polynomial gap. Because, okay, what do we have? We have a non-adaptive upper bound of k to the 3/2 and an adaptive lower bound of order k. So this is at most a gap of square root k. And so another thing to notice is that sort of these results do not rule out the possibility that adaptive algorithms just don't help us at all. That we could just make all our algorithms non-adaptive and have everything be extremely parallel and run in query complexity k log k. This is still possible. But okay, so in 2015, Cervedio, Tan, and Wright, they showed that actually adaptivity can help. And what they do is they show that testing k-juntas non-adaptively requires k log k over epsilon to the c, log k over epsilon to the c, for any c less than 1. So okay, maybe this is a bizarre expression, but plugging in the value when epsilon is some constant, we get a lower bound of k log k over log k. And this is strictly worse than what we had before. Before we had a lower bound of k log k, so it doesn't seem like we've actually gained anything. However, if we set epsilon more carefully, if we set epsilon to be 1 over log k, now the lower bound becomes k log 1 plus c k over log k. So in here, we sort of gain in two ways. In one way, we get an improved lower bound for non-adaptive algorithms. And additionally, we have that the query complexity of this non-adaptive lower bound is strictly bigger than the query complexity of the adaptive algorithm, which means that there is stuff that we can do adaptively for which we can't do non-adaptively. And for this specific case, when epsilon is 1 over log k, being adaptive helps us. Okay, so basically the new table of the results with the following results sort of beg the natural question, when exactly does adaptivity help? Since we saw this different behavior when epsilon was some constant. Sorry? Oh, okay. So we saw a different behavior when epsilon was some constant and when epsilon was this value of 1 over log k. So when does exactly adaptivity help us? And the second question is, can the adaptive algorithm be actually made non-adaptive, possibly losing some logarithmic factors, since the gap established here is at most some logarithmic factor in k. Can we lose some polylog factors and make the adaptive algorithm be non-adaptive? And in this work, we show that in fact we can. And we show that testing juntas non-adaptively requires k to the 3/2 over epsilon many queries. So while this was the sort of the state of knowledge before, now we have a nice picture of what happens for junta testing in both the non-adaptive as well as the adaptive models up to polylog factors. So we have that for the non-adaptive case, the answer should be around k to the 3/2 over epsilon. And for the adaptive case, we have the answer should be around order k up to polylog factors again. So, okay, for the rest of the talk, I want to introduce this new class of random functions, and I want to talk about how do we use these random functions to prove a lower bound of n to the 3/2 for the specific case when k equals 3n/4. So we'll want to do 3n/4 junta testing for some fixed constant epsilon. And so for general k, this will be some simple extension of our arguments, and we'll use a padding argument. And then in order to establish the epsilon dependence, you just need to be a little bit more careful in the arguments. But okay, so now I'd like to move on to talk about the random functions as well as the proof. So if you guys have any question up to now, then this is the perfect time. Okay, so we'll move on to showing the ideas behind the proof. And the proof consists of these 4 components. So we'll go through each one more carefully, but at a high level, the proof will proceed by Yau's minimax principle. So what we'll show is we'll give 2 distributions, ds and dno, both of which are supported on n-variable Boolean functions, and we'll have that the functions in ds are 3n/4 juntas, and the functions in dno are constant far from 3n/4 juntas. And in fact, what I'll actually introduce, I'll give one class of Boolean functions, and this class will be parameterized by this parameter p. And then in order to define the distribution ds and dno, I'll simply set p to specific values for ds and values for dno. So for ds, I'll set p equals to ps, and for dno, I'll set p equal to pno. And we'll set these values a little bit later. Okay, so from here we'll apply Yau, and we'll establish that there exists a deterministic algorithm which can distinguish between ds and dno, making, say, Q queries. And so the next step will be to show that these algorithms can't just do whatever they want, and in fact, because of the nature of our distributions, we have a very specific requirement that these algorithms, if they are to succeed, then they must follow. So we can put a very stringent restriction on what these algorithms can do. And okay, so from here, we'll use these specific kind of algorithms to give algorithms for an artificial problem that we define, this SSSQ problem, which is known as this set size, set queries problem, which will be parameterized by the 2 parameters ps and pno, which will correspond exactly to the values of p in the distribution ds as well as dno. So what we'll show is we'll show that if we have a deterministic algorithm which works in this particular way, distinguishing ds and dno, then we'll be able to give an algorithm for solving this set size, set queries problem for these particular parameters. And then finally, we'll want to show a lower bound on this problem SSSQ. And giving a lower bound, basically, we'll be able to run these arrows in the opposite direction to establish the lower bound for testing 3n/4 juntas. And I'll mention that this lower bound relies on thinking about the following 2 random variables. We'll think about this binomial random variable with parameter ps, and this binomial random variable with the parameter, well, with universe n/2 with parameter pno. And we'll show the lower bound will actually rely on an upper bound in the distance and total variation between these 2 random variables. So okay, now sort of we've given the high level, we'll go through each of these portions systematically. So okay, the first part is to describe the distributions ds and dno. But before I do, I want to talk about one specific function, which will be the main idea behind the way we define the distributions. So in order to define this function, I'll talk about how we evaluate this function at this particular point x. So okay, the first thing I'll do is I'll take all n coordinates and I'll split them in the middle. And then the first n/2 coordinates, these I'll call coordinates in M. And even though M is the first n/2 coordinates, I want you to think about this set M as some arbitrary set of size n/2. And then for the remainder, I'm going to split the remainder in half as well. And then consider these set of coordinates, I'll call these guys A, and there'll be n/4 of them. Okay? So in order to evaluate x, x will be evaluated in 2 steps. So in the first step, I'll look at the coordinates in M, and I'll read x only on these coordinates in M. And this will be some bit string of length n/2, since M is size n/2. And I'll interpret this string as some number between 1 and 2 to the n/2. So in particular, I want to look at x and apply this restriction not only on the variables M, and interpret this bit string as some number between 1 and 2 to the n/2, which will index to one of 2 to the n/2 many possible functions h1 through h2 to the n/2. Okay, so I have this input. I look at the coordinates in M. They're indexed to some subfunction h, and then I'll evaluate x at this subfunction. And in order to, I need to tell you what these subfunctions are. And these will be some random functions which only depend on coordinates which are a subset of A. So the way I'll do this is I'll say for each subfunction, I'll pick a set. So for this case, for h2, I'll pick a set S2, which is a subset of A, by including each coordinate in A with probability 1/√n. So in expectation, this set Si has size √n/4. And now I want to define h to be a uniform random function which only depends on variables in Si. So in order to evaluate this specific point at x, so we'll first index x into some subfunction according to M, and then I'll look at this subfunction, and this will specify a subset of the coordinates in A, and I'll look at these coordinates, and these establish the value of the function at h2. So more succinctly written, the value of the function will be given by this. And sort of it's not too hard to see that this function has to be a 3n/4 junta. Why? Because we only look at variables in M and A, and these collectively have size at most 3n/4. But now let's think about the different roles of that M and A play, and I want to talk about the influence of certain variables inside M and variables inside A. So maybe a simple thing to notice is that variables in M have extremely high influence. And why is this the case? Because each time I flip a coordinate in M, I'm automatically indexing my string into another subfunction. I'm changing the value of this x restricted on M, so it'll get indexed to some other subfunction. And this other subfunction will just use independent randomness. So new randomness, fresh randomness, and it'll, with high probability, with probability like 1/2, these values will actually disagree. So every coordinate in M has very high influence. Now, if we look at coordinates in A, in order for these to be influential, then the point has to be indexed to some function for which that coordinate is part of Si. And this happens only with probability 1/√n. So basically, each variable in A will have influence around 1/√n. Okay, and now I claim, so there's a very natural way. So we have this function, which is a 3n/4 junta. And I'll give a very natural way of making these functions not be 3n/4 juntas, and in fact being far from 3n/4 juntas. And the idea here is simply to increase the size of A by a little bit. So in particular, if now we set A to be of size n/4 plus √n, then in expectation, I'm including one more element in Si for each. And I claim that these functions are constant far from 3n/4 juntas. And the reason this is because if I need to remove the dependence on √n many variables here, then first I can remove the dependence on any of the variables in M because they have very high influence. And now each of these variables in A has influence 1/√n, and this influence is sort of spread out over all these random functions. So if I wanted to remove √n many coordinates from A, then I'll have to be changing a constant fraction of the hypercube. And so this establishes that this function should be constant far from being a 3n/4 junta. Okay, are there any questions on these two functions that we talked about? Okay, so now I'll move on to describe the distributions, and the high-level idea is that I'm going to randomize the way in which I picked M as well as the way in which I picked A. So in particular, this set M will simply be in both the DS and the D distribution, will be a random set of size n/2. And then in order to generate these sets A, for DS, I'll include each element outside of M with probability 1/2. And for Dino, I'll include each element of A with probability 1/2 plus 1/√n. Now, I encourage you to think about the case of what happens in expectation. Then in expectation, the size of DS is the size of A in DS is about n/4. And in Dino, the size of A is around n/4 plus √n/4. And even though that with constant probability, things in Dino are 3n/4 juntas, we can add some log factors to sort of fix this minor issue. But I think you should focus on the case of what happens in expectation. And this is what will happen sort of in reality by adding some log factors. Okay, so as I alluded to earlier, we can think of these two distributions actually as coming from one class of functions that's parameterized by the probability that we include a particular element outside of M into A. So in particular, this PS corresponds to this probability of including an element in A, and P0 will correspond to 1/2 plus 1/√n, which is exactly the quantity that we need to include each coordinate inside of A in D0. So okay, these will be the distribution over random functions that we'll analyze. And so this finishes the first part. And now by YAL, we'll want to say that we have some deterministic algorithm which can distinguish whether random functions come from DS or from Dino. Now I want to claim that these algorithms must work in a certain way, and they can't just do whatever they want. And the key here will be to look at the high-level structure of the function. So I want to give an example of sort of what can happen. So both these functions, both DS and Dino, they follow the structure that's outlined here. So a particular input X will first go through an indexing component, and that indexing component will feed into some evaluation component, which will evaluate the input at that particular part. So in particular, we have the indexing portion. This corresponds to the variables in M. And then the evaluation portion, these correspond to these subfunctions h1 through h2 to the n/2, which we index. So an input, both inputs go through this indexing procedure and through this evaluation procedure. And the high-level sort of idea to keep in mind is that for this class of algorithms, the indexing component will restrict the algorithms that we need to look at. So the indexing component will give a very stringent requirement that these algorithms have to go through if we want our algorithm to succeed. And then the evaluation component will be able to give us our desired lower bound. But okay, so let's think of this specific case where what happens if an algorithm makes the queries x1 through xq, and let's suppose that these queries happen to get indexed into different subfunctions hi. So maybe let's say x1 indexes into h1 and then x2 into h2 and so on. So okay, what could possibly happen? Now I claim that if this happens, then our algorithm automatically will fail. And why is this the case? Well, because the value of the function at x1 and x2, these will depend on the value of the subfunctions hi. And all these guys are getting fresh randomness, and they'll just look like random bits, regardless whether they come from DS or from Dino. So in particular, yeah.
Sorry,
yeah.
Here you're thinking of each of xi being a separate function. So
each hi, yeah, it's a separate function.
Each hi depends on a single one of the x's.
Yes, so each one of the x's gets indexed into a different subfunction. So yeah, so the queries will just be evaluated according to these subfunctions, and they'll just, since there's just one of them, they'll look like random bits. And Alice, therefore, she can't do anything. She can't say whether these queries, these values came from functions in DS or from Dino, because they both look like uniform random bits. Okay, so what Alice needs to do is that if she wants to come up with a good algorithm, she needs to ensure that multiple queries are indexed to the same subfunction. So she needs to ensure that she can focus on some particular subfunctions and work only on these subfunctions. If she gets the queries too spread out, then she'll automatically fail. So okay, what we want to do, let's suppose that Alice wants these queries to go to the same subfunction. Or let's suppose that query x1 through xl will be indexed all to subfunction h2. So what are the nature of these queries? These guys, just by definition, because they're indexed to, they must agree on all coordinates in M. Because otherwise, they would all be indexed to different things. So all these queries agree on coordinates in M. And now we can look at coordinates outside of M, and we can ask, how different can these coordinates be? So how different can the union of the symmetric difference between all these queries be outside of M? And the claim is that any two queries have to be very close to each other. And why is this the case? Let's say if two queries, let's say xi and xj, if the distance between them is large, or let's say they disagree on very many coordinates, then remember that Alice doesn't know what this hidden set M is. She has no knowledge on M, and she must come up with these queries beforehand. So it's very likely that some element on which these two queries disagree actually belongs to M. And if this happens, then these two queries will be indexed to different subfunctions. So okay, more formally, what we can show is that Alice has to set the distance between xi and xj to be at most log n. So in particular, if two queries are indexed to the same subfunction, then the distance between these two queries, the Hamming distance, is at most log n. And from here, we can say that if we have this set of queries, all these queries, then the pairwise difference, so the difference here, or the union of the symmetric difference of all these queries, has to have size at most a logarithmic factor larger than the number of queries we make. So this set T corresponds to the set of coordinates on which these values are different. Okay, and T cannot be too much larger than the number of queries. So that's the requirement of our algorithm. We must say that whenever two queries go to the same subfunction, these two queries are extremely close to each other. And this means that all the queries which go to a particular subfunction have this union of the symmetric difference being at most a logarithmic factor greater than the number of queries that we've made. Okay. So that's sort of our requirement. And from here, I'll turn to defining this SSSQ problem, the set size, set queries problem, and then we'll show how an algorithm with the restriction I just mentioned can give us an algorithm for solving this SSSQ problem. Okay, so the next slide is maybe a little dense since I defined SSSQ, but we'll go through it slowly. So okay, this set size, set queries problem, this will be a problem which deals with trying to distinguish between the size of a particular hidden set with a specific kind of queries made up of sets. That's why we call this set size, set queries. And now the problem is parameterized by three parameters, PES, PNO, and M. And this PES and PNO will correspond exactly to the parameters that we had these hidden probabilities for A. So it'll correspond to 1/2 and 1/2 plus 1 over root n. And this M will simply correspond to the universe size. So in particular, in the future, we'll set M to be n over 2. But okay, the problem wants to distinguish between the following two cases. We have a yes case, and in the yes case, we have some hidden set A, which is a random set which includes each element independently with probability P yes. Okay? And in the no case, we have a hidden set A, a subset of n, which includes each element independently with probability P no. So these will be analogous to the sets A in the distributions ds and dno. And now, for this problem, we want to distinguish between these two cases, and we have the following kinds of queries. Our queries will be composed of a particular subset of M. We'll call these queries T. And when we make a query T, what we'll get a response set V, which I think about this response set as being some very specific kind of noisy intersection. So more precisely, what will we do? We'll take this set of the query T and we'll intersect it with our random set, with our hidden set. And now we'll include each element in the intersection with probability 1 over square root of 2m. So okay, what does this mean? We'll make a query, and this query T wants to capture as much of A as possible. And whenever it does capture some elements of A, those elements will only survive with a very small probability, with probability 1 over square root of 2m. So this way we can think of V as some very specific kind of noisy intersection. And okay, in order to measure the complexity of these queries, I want to measure the cost by taking the sum of the sizes of the queries that I make. So for each, I make all these queries T1 through TQ, and then the cost of a particular algorithm for solving SSSQ will simply be the sum of the sizes of the queries that I've made. Okay, so are there any questions on this definition of the problem? Okay, so good. Now I claim there's sort of implicit dictionary between junta testing and solving junta testing for these specific distributions for ds and dno, and solving this problem SSSQ. And why is this the case? So here I've put, just to remind you, the sort of the big components of the functions on ds and dno. And now I claim that testing between ds and dno will correspond to solving the problem SSSQ with parameters 1/2, 1/2 plus 1 over root n, and n over 2. This will be because we'll pick each element of A from a universe of size n over 2. And for the yes case, we'll include it with probability 1/2. For the no case, we'll include it with probability 1/2 plus 1 over root n. This is exactly the same regime. And now, if we have these specific kinds of algorithms, and let's say this algorithm makes the queries x1 through xl, and these are indexed to a particular subfunction, hi. Now I claim that these correspond to some query sets which we'll make. And if you remember the diagram that we gave before, if we make these set of queries, x1 through xl, then this set T, the union of the symmetric difference, will correspond to exactly the kinds of sets that we want to make in the SSSQ problem. So, okay, so good. So now we have these queries x1 through xl, and this will give us some particular sets, which are the union of the symmetric difference. And then I claim that the influential directions seen in this subfunction, so these directions which we see in SI, remember hi only depends on variables in SI, this will correspond to the noisy intersection that we get from query Ti. And why is this the case? Because each SI is included with probability 1 over root n, and each element of Vi is sort of included in the intersection with probability 1 over root n. And the key here is that if we knew the response set Vi, then we can simply simulate the values of the subfunctions hi and all the inputs into all the inputs that get indexed to hi. So then it's not hard to see that the query complexity will be related to the cost, because the number of queries that we make to a particular subfunction will correspond to the size of a particular set up to a factor of log n. So more specifically, what we show is that if there's a cube query non-adaptive tester distinguishing ds and dno, then there must be an algorithm for SSSQ with these parameters, which has cost q log n, where q is the number of queries. So we only lose a logarithmic factor in this simulation. So okay, great. So we've established we have the following three components where we have an algorithm for solving SSSQ, and now what remains is to show a lower bound for this problem SSSQ. And what we show is that the problem SSSQ with parameters 1/2, 1/2 plus 1 over root n, and n over 2 needs cost n to the 3/2. And the main idea here is, like I said, to understand these random variables corresponding to the size of the hidden set A. And in SSSQ, in the yes case, the size of set A will correspond to a binomial random variable of universe n over 2, where we include each with probability 1/2. And in the case of dno, it will correspond to some binomial random variable of universe n over 2, where we include it with probability 1/2 plus 1 over root n. So now, distinguishing between these two random variables, we'll get a lower bound by looking at the distance and total variation between them. And in fact, you can show that in order to distinguish two binomial random variables with these parameters, we need around n many samples. However, each time we want a sample, each sample will cost us square root n. And why is this true? It's because each time we make a query in a particular set, regardless of whether it belongs to A or not, we'll throw it out with probability 1 minus 1 over square root n. So if we need to make root n many elements so that one of them survives and we're able to observe that sample. And in particular, combining these two facts, we get that the lower bound should be n to the 3/2. And okay, I know I brushed through it, and it takes a little bit more to formalize these ideas, but we do so in the paper, and it's not too difficult. Okay, so putting everything together, what do we get? So on the one hand, we know that if we have a non-adaptive tester for DS and dno with cube queries, then we have an algorithm solving SSSQ with parameters 1/2, 1/2 plus 1 over root n, and n over 2 with cost q log n. But on the other hand, we have that the SSSQ problem with these same parameters requires cost n to the 3/2. So putting everything together, rolling it back, we can say that testing these k juntas when k is 3n over 4, so testing 3n over 4 juntas non-adaptively requires n to the 3/2 for some constant epsilon. And like I said before, we can get the result for general k by a padding argument, and then we can get the epsilon dependence in there by just being a little bit more careful on the way we define the distribution and really tracking the distance to being a k junta. But okay, this gives the result. And in order to conclude, I want to conclude with some open problems. And in particular, so there's this nice concept that's introduced by Cannon and Gore, in which they talk about different levels of adaptivity. So how we can, say, have an algorithm which is not fully adaptive and not non-adaptive, but rather have these algorithms proceed in a fixed number of rounds. So it'd be nice to understand some possible trade-offs in junta testing of how many queries do we need if we're allowed to make a certain number, let's say R rounds, where R is maybe greater than 1 but less than Q. And then, so another problem would be to try to understand other natural properties of Boolean functions which have gaps or which don't have gaps between their adaptive and their non-adaptive query complexity. So like I mentioned, there are some natural properties which have exponential gaps, and there's very many natural properties for which we still don't know. So one particular property I'm very interested in would be for monotonicity. So can we show that sort of adaptive algorithms are more powerful or not more powerful than non-adaptive algorithms for monotonicity testing? And lastly, it'd be nice to see more applications of this class of random functions, in the sense that it seems like this way of thinking between an indexing portion and an evaluation portion helps make our proofs for lower bounds a lot simpler. So it'd be very nice to see more applications of these ideas. But that's the end of my talk. And if you have any questions, then this will be the perfect time.
Okay, thanks, Erik. So we have time for questions. Okay, maybe to get us started, I have a simple question. So I'm not familiar with the upper bound that your lower bound matches.
Mm-hmm.
Is it easy to say what it does? And is there any intuition from your class of functions that comes from trying to understand what that algorithm does?
Yeah, so the non-adaptive algorithm, which our lower bound makes tight up to polylog factors, what we do is the algorithm, it tries to sort of estimate this quantity called, so the first thing it does is it splits these coordinates into like k squared many blocks, into blocks of coordinates, and then analyzes each block separately. But in our case, and sort of our hardest case to show the lower bound is when k is order n, then in some sense, basically what the algorithm would do in this scenario will simply try to estimate the lack of influence in any particular one of the variables. So, I mean,
so it would do it one variable at a time and then consider that variable and make like square root n queries to try to determine if it's an influential variable?
Yeah, so if you look at okay, there's, in the non-adaptive algorithm, it's sort of these two different algorithms which have this like sweet spot where if you have a gap of square root n many more variables in the far case with influence each 1 over root n, this is like exactly the hard case. And sort of this is what we do for our evaluation part. These queries and try to determine whether the influence in each one of these coordinates, and it would try to determine whether the influence is greater than 1 over root n or is 0.
Yeah.
But yeah, basically our lower bound says that you can't do anything than query sort of paths of length log n, which just loses a logarithmic factor if we make all queries to all possible, like an edge to possible edges. That's sort of my high level intuition.
Thanks. Other questions?
So the non-adaptive algorithm for junta testing, so it doesn't identify the variables or a potential list of influential variables per se, right? Because that would definitely require like some log n dependence or something like that, right? If you want to index them somehow.
Yes, yes. But I mean, if we were only focused on the case where k is order n, then we would be allowed to go through each variable.
I see.
Right? For the case when k is much smaller than order n, then you do need like some like clever partitioning of the variables and work with groups of variables.
So if there's no other questions?
Yeah, that's a question. Okay. I remember like mentioning that vaguely at some point, but have you considered maybe if there was a reformulation in terms of communication complexity of your hard instance, or maybe the SSSQ problem? Because I mean, if I'm not mistaken, like the other lower bounds, like the omega of k for the adaptive case, are based on a communication. I mean, some of them are based on a communication complexity reduction. And is there such a thing that maybe you could cast your lower bound in some framework like that?
Maybe, I don't know. Yeah, maybe there is a way to think about this via communication complexity, but yeah, I'm not sure.
Okay. There's no more questions for Erik? Okay, in that case, we're going to go offline, but anyone who wants to hang out for a little bit